All right, guys. So welcome back. In this video, we're gonna start discussing chapter 5 materials. Um, we're gonna start out with 5.1, and the title is antiderivatives and indefinite integrals. Um, so up to this point, we learned how to differentiate a function first and the second derivatives. We also look at application of first and second derivative of a function. In this chapter, we're gonna kind of take a step back and go in the reverse direction. So instead of differentiate a function, we anti-differentiate a function, and it turns out a little more complicated to go backwards and go forward, and that's how usually things are in real life. So anti-differentiate or anti-derivatives are just, you kind of given a function and you ask, okay, what function that we take the derivative that give this function. So the definition we have here is saying that a capital F function, so big capital F, is considered to be an anti-derivative function of the lowercase f if we take the derivative of capital F function and we get the lowercase f function. So, if this is the case there, then this function f itself is, anti-derivative function of the lowercase f. So that's pretty much what the definition is saying. But let's start out with an example here. So let's consider a function. Let's consider a big capital F function to be x to the third over 3. Okay. Then will you say that capital F prime, or the derivative of this function, is just x squared? All right. So power rule said that 3 comes down, so 3 times 3. 3 over 3 is 1, so subtract the power by 1, so that gives us x squared. So in this case here, we can call this function here is a lowercase f of x. So we have this case here, we have f prime of x equal to lowercase f here. So that implied that this function here, x to the third over 3, is an anti-derivative function of the lowercase function f of x, and that is x squared. Notice that we use the word is a antiderivative or is an antiderivative. It's not the antiderivative functions. And let's take a look at why it's not the antiderivative of the function x squared. Okay. Now suppose, what if we have these functions? We have let's call this two functions. Let's call this h of x, x cubed over 3 plus 2, and let's call this g of x here, x cubed over 3 plus square root 5. Okay. What about these two functions here? What if we given these two functions and we ask to find their derivative? Okay, well, that's h prime of x is just going to be x squared there. The constant 2 is going to be 0. And then g prime of x is also x squared. Square root 5 is constant, so the derivative of that constant term is going to be 0. So look at this. So we have the derivative of these two different functions. So h of x and g of x are two separate functions, different by a constant. And those two produce the same derivatives, x squared. So in this case here, we say that both h of x and g of x are anti-derivatives of the function f of x equal x squared. So that implies that anti-derivative of a given function is not unique. It's not just one antiderivative, but it's actually more. How many more? How many more? It turns out the answer to that is infinitely many more. Infinitely many anti derivative. Okay, so to capture that concept, we would say that, we would say that the antiderivative of a given function is a in this form of, we call this the general solution, or the general a form of derivative. So we say that x cubed over 3 plus some constant c. We said this is a general derivative, or general solution, or general derivative, excuse me, antiderivative of x squared function z. Okay, so this itself is we call this is a family of antiderivative, because if c is a constant, there, c can be any value. So each of this derivative is differed by a plus c. So that c could be positive 3, positive 2, square root of 5, pi, negative 2, whatever, right? So the antiderivative of a given function, this x squared function here, is, it's more than just a single function. It's a family of antiderivatives. The way we capture that, we say that it's a function that is x to the third over 3 plus some constant. Okay, what does that look like in terms of the graph? Okay, well, in terms of the graph, if I sketch these antiderivatives, they look like this. So suppose we have this x and y coordinate system here. So x to the third over 3, that's a cubic graph with a stretch factor of 3. So they're going to look somewhere around, something like that. Okay, so that's one antiderivative, because this is when there is no y-intercept, or it just is no constant. That's just x3 over 3 plus 0, because the 0 is right there. And then if we're looking at x3 over 3 plus 3, for example, then that's going to shift up 3 units. So we're looking at, maybe something like that. Or if it's shift down 3 units, maybe something like that. Okay, let's use a different color here. Or maybe it just shift down 1 unit, or up 1 unit, or whatever, right? So you get the point. So all of these here are antiderivatives of x squared. Okay, so all those are antiderivatives of x squared function. Okay, so it's not just one antiderivative, but it's infinitely many antiderivatives, and we capture that concept of infinitely many by just assign that plus c at the end. So each antiderivative of x squared function is differed by a constant c, okay, and that constant c could be any real number. Know that it's not a variable. Okay, so that's the difference there. So I want to end this video on a new notation that we're gonna learn in this lesson, and that new notation is called indefinite integral. Okay, so this squiggly line here, right, I'll write a little bigger. So that notation there is, this notation is the integral, right? The integral notation. I think I spelled integral wrong. So integral notation. And anytime we see that notation, okay, that notation means find the antiderivative. Okay, so that squiggly line there is called the integral notation, and anytime we see that, immediately the math process, what we're supposed to do is find the antiderivative. Find the antiderivative of the function inside the integral. We call that is the integrand. Okay, so let's go back from the beginning. The definition for indefinite integral is say that this notation here, this integral of f of x dx, this is called the indefinite integral. This represents the family of all antiderivative of f of x, and f of x is called the integrand. The symbol dx indicates the anti-differentiation process is performed with respect to the variable x itself. Okay, so later on we'll learn a little more about what dx mean, more explicitly. But as of right now, anytime you see an integral followed with f of x dx, that means, hey, find the antiderivative of the function, f of x with respect to x. Later on, we look at multiple variables. It's important that we know what variable to integrate, which we'll find the antiderivative with. So it's important the dx is there. So the answer for this here is the antiderivative of the function f of x, and call that the capital f of x, and plus some constant c. So an example to kind of show this notation is we just did that. We said, okay, what was the antiderivative of the function x squared? So that's our f of x there. Well, that antiderivative was x to the third over 3. And then, is it just 1? No, it's infinitely many. We're going to distinguish the difference between those antiderivative by a constant c. Okay. So that is, usually we're given problems of indefinite integrals in this form, and we ask to get to this form there. And so this will be the answer itself. Okay, so I'm going to go ahead and end the video on this note here. And then in the next video, we're going to look at many examples and more rules, just like the derivative rules. Anytime you give a function, you ask to find the derivative. In this chapter, anytime you're given the integral, we can use certain rule according to certain function to find the antiderivative. So we will discuss that in the next video.